That is, according to Airy model, he said the height, the mountains, the equilibrium were achieved by variation in crustal thickness. You can see in order to accommodate the height of this mountain, the mountain has roots in the asthenosphere. You can see this area of the crust where there are no mountain, it is flat. You can see that the base is also flat. And that is what we have here. That for equilibrium to be achieved, you can see this one is tall. This is it. You can see. It said all of them have the same density. You can see the same density, 2.8, 2.8. But anyone that is taller, like this yellow, is also the deepest. If this one is taller than this, it must also be deeper than that. All of them have the same density. That is for Airy model. For Pratt model, he said, no, the base, whether you have a mountain or you have the lowland, their bases are the same. You can see the bottom is flat. Unlike the Airy model, in which the bottom of mountain or the bottom of the crust mimic what is on the surface. This place is flat, the bottom is flat. This place extends into the atmosphere, it extends deeper into the asthenosphere. So, but no, Pratt says, no, that is not how equilibrium is achieved. That equilibrium is achieved if by different rocks having different density. Don't forget, Airy said the rocks, the crust have the same density. But Pratt says no, the crust has different density. And it is that different density that compensates for the variation in height of mountain. He said the base of everything is flat. And that is what you see here. You can see the base is flat here. But different rocks or different part of the crust has different density. The third one, the third one is what we call the Venn or Fletcher isostacy model. What the guy is just saying is that if you put a load like a mountain on the crust will bend. That the load, pressure of the load is distributed over an area. Where the load is uppermost, you can see it bend the most. Whereas the load is diminishing, the amount of bend is also diminishing. So, again, I go over it again. Airy hypothesis or model says the crust, which is the rigid upper layer, and substrate are assumed to have a constant density. So, this is sea level. This is above the surface. High density. The white, you can see this mountain. In order to attain equilibrium, it has a root, which we call crustal root. The crust or the lithosphere is essentially of low density, and the root immerses into the high density asthenosphere, and there is depth of compensation. So, according to Airy, isostatic compensation or equilibrium is achieved by deep roots, just like the phenomenon of iceberg. When they will say in English, they will say, what you are seeing is a tip of the iceberg. That Once you see an iceberg floating, a lot of it is under the water. What you are seeing on the surface is just one part of it. Pratt model is saying the depth of the base of upper level is constant. This is the base. That isostatic equilibrium is achieved by composing the upper layer of column of constant density. Each of these columns has different density. Is that what? So, are you asking me a question?
Yes, sir.
Okay.
Sir, can you please go back to the other slide?
Okay. This one
Yes, sir.
Yes, sir.
or this one?
Thank you, sir.
1,000.
You want to ask me? You want to ask me a question? Okay. Now, again, this is the Pratt. Pratt model, Airy model. Airy model was mostly correct about what support large wide mountain. But it took until 1970 to prove this with seismic work that measured the thickness of the crust and lithosphere beneath mountain. It was during this time that we discovered that, based on Airy model, that mountain definitely has roots. Pratt was correct in that the difference between the low straddling ocean basins and the high standing continents is partially due to the fact that oceans have okay. Ikebudu Michael, what's your question?
Sir, it couldn't.
Okay. Iku Deyibu. Okay.
You said that you said that they proved Pratt's theory using seismic work. What is
Yes.
that seismic work?
It's a method in geophysics which we are going to do later on, maybe in 300 or 400 level. We should send signal, shock wave into the subsurface. And by the time they come back to the surface, they bring information about the subsurface for you. That is what we call seismic method or seismic work. Is that okay?
Yes, sir.
Yeah. So again, this is another way to illustrate Pratt and Airy isostacy. For the very mainness of flexural model, this hypothesis was suggested to explain how large topographic clues such as seamounts. Seamount is a short version of sea mountain. So a seamount is a mountain rising from the ocean floor that does not reach to the water surface or sea level. So, and thus it is not an island, so to speak. It is when it extends above the water surface into the atmosphere, that is when you call it an island. But when it does not reach the surface of the water, we call it a seamount. So, because it's not an island, because it does not extend to reach the water surface and can be compensated by regional rather than local displacement of the lithosphere. This is the more general solution for lithospheric flexure as it approaches the locally compensated models. So, this is the, what should I call it now? The figure that explains flexural model. All that is saying, unlike the other one, that unlike the Airy model, in which if you have a mountain, the base will also be like that. The base or the root will mirror what is on the surface. Just like this black one. If it is a airy model, the root will have been like this black figure here. But for for flexural model, Venn-Menes model, to compensate for this mountain, it will be this blue line, such that the load is distributed beyond the area where the mountain on the surface cover. So it just says the load is distributed over a wider area compared to what you have in airy model. Airy model has local compensation, which is this black line, whereas Venn-Menes or flexural model has what you call regional compensation. The load is spread over an area. So in case of the Venn-Menes compensation, model, the lithosphere flexes. That is why we call it flexural, under its own weight, and shields the asthenosphere from the difference in pressures. Some of the features of the isostacy will be discussed now. Isostacy can affect mountains. That is, a mountain that we saw maybe 40, 50 years ago might have grown taller, or it can grow shorter. It can grow taller or can grow shorter. So isostatic adjustment also occur in areas where river carrying a large load flow into large bodies of water, such as an ocean, where you have large sediment being brought from the hinterland and being deposited in the ocean. It can make such a place to be going down because of the heavy load that is involved. Isostatic adjustment can also occur as a result of growth and retreat of glaciers and ice sheets. If you have glacier, big ice being formed in a particular place, it will constitute extra load in that area, and it can cause that area to be sinking. If you have an area where you have, on the other hand, you can have an area where there is a large mass of ice, and the ice melts to water, and the water flows away, then it can cause that area to be rebounding. That is, since you have relieved it of the weight or the load, the area can be rising. The weight of the ice causes the lithosphere to sink, while the ocean floor rises because the weight of the overlying water is less. When glacier or ice sheet melts, the land rises and the ocean floor sinks. These are examples of what we are talking about. So what we call orogeny is process of mountain building. Let's look at this situation in which these two continents collide. When they collide, the two of them will form a mountain. And you can see the mountain. And we call that process orogeny. After some time, that mountain will be eroded. After the erosion, the sediment will move to the sides. And you can see the mountain will be rising. More erosion, rising, and that is what we call rebound. Erosion, rebound. So what we have here is a more pictorial representation of what here. You have the mountains. As the mountain is sinking, you have displacement of the upper mantle when the mountain is sinking. Because, and what is causing the mountain to be sinking is because of intrusion you have here. That constitutes more load. When the mountain begins to erode, instead of it sinking, it begins to rise until equilibrium is achieved. So that is what you call isostatic. That is how isostatic adjustment is achieved in orogeny. Like I said, orogeny is mountain building. In volcanism, like in the Hawaiian Islands, when you have volcanism or materials magma being brought and emplaced in a particular place, where you have load, there will be crustal depression. I can look at a situation in which you have ice here. The ice causes depression. The mantle material moves to the sides. After some time, the ice melts. Because there is no load, instead of the crust sinking, the crust will begin to come up until it attains equilibrium. That's what we call glacial rebound. You see, the same thing, just like I explained, glacial ice is here. The load is now causing the crust to sink. After some time, the ice melts. It creates a depression. And you can see it begins to rise until depression disappears. So erosion and resulting isostatic adjustments of the crust. So you can see uplift. It was here before, it moves up just because this place is eroded. There is need for us to differentiate, for you to understand this concept clearly. The first one is what we call uplift. Uplift is when the surface raised up relative to the flat topography around it. And it's usually caused by a rebound. When load is removed from a section of the earth, such as melting of ice and such as erosion of mountain, that's what is called subsidence. That occurs when surface is lowered relative to the reference point. And surface can be lowered when you have deposition of sediments or when you have formation of new rock, as in volcanism. So subsidence and uplift are word and opposite. So let's also look at exhumation versus burial. Exhumation is when a rock that was buried before begins to come to the surface. Whereas burial is when rocks that used to be seen on the surface begin to sink and move away into the subsurface. Irrespective of whether you have an uplift or subsidence. So can you ask me a question on what? So we have finished. Have you been able to get this content from your course advisor? Hello, class. Are you sleeping?
No, sir, I didn't hear that.
Class, sir.
Sir, which content is that?
This course. What is the title of this course?
GPH 111.
Physics of the earth.
Physics of the earth, sir.
Physics of the earth. So somebody asked me for the course content. I said, your course advisor should have given you the course content for all your courses.
Yes, he has.
Okay, so this course content, if you look at the course content of this, what I taught you is measurement of, gravitational field, and measurement of gravitational field, and isostacy. That is what I've just taught you now. We still have 5 other lecturers that we teach you. Other topics, 5 or 6 other lecturers that we teach you. So the topics that are supposed to teach, that's what I've just taught now.